Let's talk about a process you've probably never heard of, but one that is, and I mean this literally, all around you. It's called steam cracking, and it's the secret behind your phone, your food packaging, and so much of what makes our world, well, modern.
So, let's just start with a basic question. Have you ever really thought about how a barrel of thick, black crude oil gets turned into, say, the clear plastic bottle you're drinking from? How does one become the other? Well, the answer, as it turns out, is all about breaking things.
And that brings us to our first big idea, this need to crack stuff in the first place. What does that even mean?
Okay, so here's the deal. Our entire plastics industry, pretty much the whole thing, is built on a couple of tiny, super important molecules, ethylene and propylene. You can think of them like chemical Lego bricks. We snap them together over and over again to build everything from saran wrap to car bumpers. But here's the catch. When we get raw crude oil from the ground, it has almost none of these little guys in it. So, if the building blocks we need aren't just lying around, we have to make them. And our starting ingredient for this whole recipe is a substance called naphtha.
So what is naphtha? Well, think of a crude oil refinery like a giant kitchen. Naphtha is just one of the ingredients you get from the main pantry, which is the crude oil itself. It's what's called a light fraction, which just means it's a liquid mixture of molecules that aren't quite ready for prime time.
And the key thing to see here is that naphtha isn't just one thing. It's a whole cocktail of different molecules. You've got pentane with 5 carbons, hexane with 6, all the way up to molecules with 12 or more carbons. And these things are just way too big and clunky. They're not the tiny Lego bricks we need. So what do? We've got to break them.
Which brings us to the main event. We have these long chain molecules and we need short ones. So, how in the world do you actually break a molecule?
The goal is super simple, right? We take a long, tangled necklace of hydrocarbons and we snap it. We want to break it into smaller, much more valuable pieces, those little ethylene and propylene molecules we're after. But here's the thing. Breaking chemical bonds isn't random. There's a real science to it.
And this leads to a fascinating question. If you look at one of these molecules, you'll see it's held together by all sorts of bonds. Bonds between carbon atoms and bonds between carbon and hydrogen atoms. So when you start heating it up, which of those links is going to snap first?
And the answer, it turns out, is all about energy. Just like with a metal chain, it's always the weakest link that breaks first. And if you look at the numbers, it takes way less energy to break the bonds between 2 carbon atoms than it does to break a carbon-hydrogen bond. So when we crank up the heat, it's the carbon backbone of the molecule that's going to crack right open.
Okay, so we know which bonds are going to break. But there's a much bigger question we have to ask first. Do the laws of physics even let us do this? And that brings us to the science behind the split. I mean, this is the very first thing a chemical engineer has to figure out. Is this reaction what we call thermodynamically favorable? Or, to put it simply, will nature even allow this to happen?
Now, without getting bogged down in the math, there's a really cool principle at work here. Nature loves chaos. It loves disorder. And breaking one big organized molecule into a whole bunch of smaller, messier ones, that is a massive increase in chaos. And it turns out, at really high temperatures, that drive towards chaos is so powerful that the laws of physics basically give this reaction a giant green light.
But, just because something is possible doesn't mean it's useful. I mean, for a giant industrial process that has to churn out millions of tons of this stuff a year, it also has to be fast. And this is where we move from whether it can happen to how quickly it happens. And this graph tells the whole story. See that blue line shooting upwards? That's the first most important step, breaking that very first carbon-carbon bond. It has what we call a high activation energy, which is like a huge hill the reaction has to climb to get started. The only way to get those molecules over that hill is to hit them with an incredible amount of heat. Temperature isn't just helping here, it's the accelerator pedal, and we're slamming it to the floor. So, we know we have to heat naphtha to some seriously extreme temperatures. Let's take a look inside the gigantic industrial furnace where all this magic happens, the steam cracker. Now, trying to run a reaction at over 800 degrees Celsius comes with some massive problems. One of the biggest is an unwanted side reaction that makes pure carbon. We call it coke. And this stuff is a nightmare. It builds up on the inside of the reactor pipes, acting like a thick blanket that blocks the heat and can eventually just clog the whole system, forcing a really expensive shutdown. So how do you solve a problem like coke buildup? Well, the solution has been hiding in plain sight this whole time. It's right there in the name of the process. You use steam.
Steam is amazing because it does two critical jobs at once. First, it dilutes everything. By mixing steam in with the naphtha, you spread out the hydrocarbon molecules, which actually helps push the cracking reaction forward. But here's the really clever part. The steam acts like a cleaning crew. It actually reacts with that nasty carbon buildup and turns it into harmless gases, essentially scrubbing the pipes clean while the whole thing is still running.
So when you put it all together, the whole industrial process is a pretty wild ride. First, you mix the naphtha and steam and heat them up. Then, that mixture gets blasted into the cracking furnace, hitting almost 850 degrees Celsius for just a split second. Then you have to stop the reaction instantly. It's called a quench, to lock in all the good stuff you just made. And finally, that whole messy mixture gets sent off to be separated into pure products.
So why go to all this trouble? Why the extreme heat, the steam, the whole shebang? Well, it all comes down to what you get at the end. Steam cracking is specifically tuned to produce a massive amount of ethylene, up to 30%. That's the most valuable Lego brick of them all. Other processes, like catalytic cracking, they run cooler, sure, but they make way less of the stuff we actually want.
And there it is. That's the whole journey. We've gone from a barrel of crude oil to a fraction called naphtha. We've blasted it with insane heat inside a steam cracker, all to create those fundamental chemical building blocks that really form the foundation of our material world.
You know, steam cracking is an absolute triumph of chemical engineering. It's a high-energy, incredibly precise process that makes modern life possible. But it also uses a staggering amount of energy. So the next great challenge, the question for the next generation of engineers, is how do we reinvent this essential process for a more sustainable future? What does the steam cracker of tomorrow even look like? That's a question we're all going to have to answer together.